For centuries, electricity was envisioned as an invisible, continuous fluid that flowed seamlessly through physical matter. The first and most popular theory, championed by early pioneers like Benjamin Franklin, was that electric charge was a single substance that could be infinitely divided and shared. The second and far more radical theory was that electricity was actually granular, made up of discrete, indivisible chunks of charge that would simply be too infinitesimally small to ever isolate or measure directly. In 1897, J.J. Thomson tried to solve this mystery with the aid of a cathode ray tube. By bending glowing electrical beams with magnets, Thomson successfully calculated the mass-to-charge ratio of the newly discovered electron. However, he was stuck with a mathematical fraction, completely unable to extract the exact value of the charge itself. While trying to take the next step, an associate named John Seely Townsend attempted to measure the raw charge by observing electrically charged water clouds in a laboratory. Townsend tried to calculate the falling speed of these tiny water droplets, but because water evaporated so rapidly under the hot lab lights, he could not reach any stable or discernible value, leaving the definitive size of nature's fundamental spark a complete unknown. This frustrating hurdle would stall physicists for over a decade. But the first true measurement of an individual quantum of charge would come in 1909. When an American physicist would have a brilliant burst of experimental ingenuity that would secure the exact value of the electron. Robert A. Millikan was born in Morrison, Illinois, in 1868. Little is known about Millikan's early struggles in physics other than the fact that he initially taught himself the subject while working at Oberlin College. His true scientific breakthrough came later while working as a professor at the University of Chicago. In fact, Millikan made his key discovery with the help of a brilliant graduate student named Harvey Fletcher. Millikan and Fletcher, while toiling in the Chicago labs, realized that Townsend's fatal flaw was using a liquid that evaporated, and therefore they had the opportunity to perfect the experiment by simply switching to something far more stable, heavy machine oil. In 1909, Millikan and Fletcher began constructing a beautifully elegant apparatus. They used a standard perfume atomizer to spray a fine mist of oil into a transparent chamber. After falling through a tiny hole, these microscopic droplets entered a space between two parallel metal plates. Millikan had been using an intense light beam to illuminate the droplets, making them look like tiny glowing stars through his viewing microscope. He noticed something peculiar when he applied a high voltage to the metal plates above and below the drops. Because the droplets had picked up a static charge from the friction of the atomizer, the electric field would push upwards against them, fighting the downward pull of gravity. Millikan could come to two main conclusions after observing this phenomenon. The first was that by carefully adjusting the voltage dial, he could make a single droplet hover perfectly still in mid-air. The second was that by turning the voltage off and measuring how fast the drop fell, he could mathematically determine its exact mass. To try and figure out the fundamental charge, Millikan began studying hundreds of these hovering droplets one by one. Later on, Millikan documented his exhaustive results, where he explained them using a simple balance of classical forces. When gravity pulls an oil drop down, the electrical voltage pushes it up. If the drop hangs suspended, the two forces are perfectly equal. Since he knew the exact voltage he was applying, and he had just calculated the mass of the drop from its falling speed, he simply had to solve for the missing variable, the total electrical charge on that specific droplet. So, Millikan just needed to calculate the charges of many different drops, and compare them to see if a predictable pattern emerged. Millikan found a stunning mathematical relationship. The charges on the droplets were not randomly distributed. Instead, they were always exact multiples of a single, baseline number. Combining this with his incredibly meticulous observations, Millikan concluded that this base number was the elementary charge of a single electron, roughly calculated at 1.592 times 10 to the negative 19 coulombs. You could have a droplet with 2 extra electrons, or 3, or 10, but never 2.5. Most of the slight error in Millikan's original calculations was attributed to one main correlated assumption. The calculated value for the viscosity of air at the time was slightly incorrect, meaning his calculation of the droplet's mass was roughly 0.5% off. Millikan published his groundbreaking results in a famous paper in 1913. About a year after Millikan's work brought to light the first experimental evidence of the quantized electron, Austrian physicist Felix Ehrenhaft fiercely attacked the findings using an entirely different method, observing microscopic metal dust instead of oil. Ehrenhaft's intention was not to validate the elementary charge, but rather to find evidence of fractions of an electron, which he called sub-electrons. Ehrenhaft figured that if he were to measure much smaller metallic particles, it would disprove the theory that electrical charge had a strict, indivisible limit. Millikan himself had observed tiny anomalies in extremely small drops, but realized that Brownian motion, the random jittering of air molecules, made them too imprecise to firmly rely on. Ehrenhaft was indeed able to find a chaotic spread of data points, uncovering what looked like a continuous spectrum of charge. But with some genius insight and rigorous retesting by the scientific community, physicists eventually determined that Ehrenhaft's weird subcharges were entirely due to experimental errors, optical illusions, and irregular particle shapes. When perfectly spherical oil drops were used, the charges were inextricably linked to whole numbers. The defense of this fundamental law by Millikan not only provided the first direct evidence that charge is purely quantized, but also allowed him to win the Nobel Prize quite decisively. He determined that the elementary charge is a physical reality, clearing up centuries of electrical confusion. The evidence provided by the oil drop experiment was crucial in determining that electricity is not an infinitely divisible fluid. There was still a need to refine Millikan's exact decimal points, led mainly by scientists who knew the viscosity of air was causing slight rounding errors. They believed that these tiny anomalies could be bypassed entirely by observing matter on an atomic scale. In the late 1920s, Swedish physicist Erik Becklin used a completely different experimental approach involving X-ray crystallography to further refine the elementary charge. Up until this point, all of the detailed probes of the electron's charge had been somewhat limited by observing macroscopic droplets floating in air. No one had yet successfully measured charge by isolating the precise geometric spacing of atoms themselves, for no one had a strong enough X-ray apparatus, or if they did, they didn't have the technology to manifest that experiment into reality. Once the first theoretical models of atomic crystal lattices were accepted, though, many scientists realized to what degree of fundamental geometry they were working with, and therefore realized the grand scale at which they needed to make an experimental apparatus. Becklin was among the first to successfully use such a dedicated setup, and subsequently discover the exact charge based off of measuring perfectly grown calcite crystals. Becklin's setup went as follows. He used a specialized vacuum chamber with an X-ray source. In front of this source, he placed a precise crystal target, and directly behind that, a photographic plate. He then began bombarding the crystal so that a highly penetrating beam would diffract off the atomic layers and strike the plate. The angles of diffraction would be seen when they entered the detector, and wouldn't be seen clearly if the atomic spacing wasn't perfectly uniform. Becklin then began to analyze the geometry of these scattered rays, calculating the exact distance between individual atoms in the crystal. By combining this microscopic distance with the macroscopic density of the material, physicists could perfectly calculate Avogadro's number. Then, by dividing the total charge of a mole of electrons, known as Faraday's constant, by Avogadro's number, his calculations yielded a far more accurate value for the single electron charge, solving the final missing decimal points of Millikan's era. Most of the measurements of the electron up to this point have been close to accurate with less than 1% of error, but they have not been perfectly precise to modern standards. Most of the early values rounded off the deeply fundamental quantum constants. Unlocking the final, absolute exactness of the elementary charge would require observing electrons moving in purely two-dimensional planes. This technology would not come until the late 20th century, and would come at the hands of modern quantum physicists studying the quantum Hall effect. German physicist Klaus von Klitzing is known more famously for his 1980 discovery of the exact quantization of electrical resistance. It is one of the most brilliant precision measurements in solid-state physics, providing strong evidence that electrical resistance in a specialized semiconductor jumps in perfectly mathematical steps dictated purely by the electron's charge. Klitzing was a pioneer in precision quantum instruments and had been brainstorming ideas of how to isolate electron behavior under extreme magnetic fields. He started with trying to find ways to extract a pure reading of electrons squeezed into a microscopic, flat layer using massive superconducting magnets and dropping the temperature of the samples to near absolute zero. Still, isolating a single electron required incredible exactness. The next and final efforts would continue into the 21st century and wouldn't reach peak manipulation until the advent of single electron transistors. For these later attempts, scientists invented a new and incredibly clever device. This device was essentially an ultra-cold microscopic turnstile. Perhaps the most impressive aspect of this tiny gate was not its microscopic size, but the fact that the entire circuit was made to perfectly pump one single electron through the circuit at a time using high-frequency microwaves. Physicists, frustrated with relying on billions of flowing electrons in previous years, wanted thermal noise to have absolutely no effect whatsoever on their current measurements. Inside the transistor were an array of quantum dots that trapped electrons successively, moving them forward billions of times a second. This setup was able to perfectly isolate the individual charges before they hit the detector. Today's scientists use these incredible devices at modern metrology facilities to get the most precise standard model parameters they can. These extreme cryogenic systems are not completely immune to error either, as they are still prone to quantum tunneling glitches, which can shift the current momentarily at times. Regardless, the modern results derived from these quantum devices have locked in the elementary charge permanently. In 2019, the scientific community made a monumental decision. They redefined the ampere and set the exact value of the elementary charge to precisely 1.60217663 4 times 10 to the negative 19 coulombs, with zero uncertainty. It's astounding how well Millikan's initial hovering oil drops worked, and how it was the primary method of conceptualizing charge up until quantum gates and crystals were designed. Today, the exact charge of the electron is set as a fundamental pillar of the universe, and our understanding of everything from chemistry to electronics is heavily reliant on this deeply immutable constant. This means that today, measuring the electron does not just impact the accepted behavior of an atom, but rather forms the absolute baseline for all modern technology. The electron's charge is incredibly tiny relative to our macroscopic world, but when combined in the billions, its potent nature is exposed. It's the spark of our entire modern era, and unlocking its exact value is a prime example of pushing experimental physics to its boundaries. The sheer fact that scientists in the early 20th century were able to take what seemed like an unmeasurable, invisible fluid before and turn it into a perfectly quantized foundation of matter is beyond remarkable. Thanks to decades of innovation and the relentless work of many brilliant physicists, our understanding of electricity has grown significantly, along with the fundamental forces that hold our universe together. If you enjoyed this video, please consider liking and subscribing. Click here if you want to see more scientific progress made during this time period. Thank you for watching, and I will see you in the next video. This video is brought to you by the Deepstash app.